Hydration enthalpy, actually when you put an ion into water, it gets surrounded by the water molecule, and because it gets surrounded by the water molecule, okay, there is a lot of energy which is released, heat which is released, okay, and that's it, that is known as hydration energy. And we discussed last time that hydration energy is directly proportional to the charge of the cation, because if the charge is more, attraction will be more, right? Charge is more, attraction will be more, and more heat will be released. And if the ion is smaller, if it is smaller in size, then also attraction will be more heat will be released, right? And that heat is known as hydration energy. Okay, and last time we have seen that in lithium the hydration energy was maximum, right? It is because lithium was smallest, okay, and cesium was biggest, but because it was biggest, it was not able to attract water molecule on itself. As a result, cesium was not hydrated by more extent, lithium was hydrated, and we have seen that there were layers of water molecule which deposited on lithium, and due to which the lithium became very, very large, and that was the radius of the hydrated ion, right? That's what we discussed. Okay, so let's continue ahead. Okay, so in lithium, what happens is it forms hydrated salt. What do you mean by hydrated salts? Any idea? Fatima?
No, sir.
Okay, no problem. We will discuss it. Lithium salts are hydrated. Hydrated means if you keep, suppose lithium salt, we use NaCl, right? That is a common salt, okay, which we use in our food. And the lithium salt will be similar lithium chloride, let's say. And if you keep it in air for some time, it will absorb moisture from the air, okay, and it will absorb moisture, and it will not turn into solution, right? It will absorb in the moisture, it will not turn into solution, it will remain solid only, okay, and it absorbs water in its crystal itself, okay, the crystal will remain as a crystal, and but between the cation, lithium cation, and Cl minus anion, these water molecules are going to get deposited, right? Li plus, Cl minus, Li plus, okay, Cl minus, similarly this Cl minus, then you have Li plus. So these water molecules will get deposited, okay, in these, between these ions. And you might have observed that when there is a rain, okay, the salt which we use for cooking and all, that form lumps, you might have noticed, and it is that because of the absorption of water, okay, it form hydrate. So lithium being smaller, it will have maximum tendency to attract water molecule, so it will form hydrate, okay. And this hydration energy which is released by the cation and anion is also responsible for dissolution of the salt in water, right? For example, NaCl is there, sodium chloride. Sodium chloride, and you might have seen this. This is a very common thing. When you put it in water, stir it with a spoon, it get dissolved, right? So when you put it in water, it become Na plus aqueous, okay, and Cl minus aqueous. Okay, Na plus aqueous and Cl minus aqueous get dissolved in water. Okay, and why a salt is dissolved in water? While there are some salts like silver salts are there, silver chloride is there, that will not get dissolved in water. Okay, so if someone asks you, okay, it will be applicable everywhere. Just remember one thing. If someone asks you that why a salt is dissolved in water, why a salt or why a salt is cannot be dissolved insoluble in water. Okay, actually it consists of two things, right? So let's imagine that first you give some energy to this NaCl solid, and this energy is known as lattice energy. Lattice energy. Okay, lattice, this salt, uh, each cation is surrounded by anion, each anion is surrounded by cation, and that framework is known as lattice. Okay, so when you give this much energy, lattice energy, it breaks all the cation and anion break, and what you get is you get sodium plus, which will be in the gaseous form, and Cl minus, that also will be in the gaseous form. Okay, actually, while dissolving NaCl, we don't give these energies one by one. Okay, but while thinking, we have to think them as one by one so that we can understand them properly. Okay, so actually, when you put NaCl in water, it dissolves, and the Na plus ion, Cl minus ions get separated from one another. Okay, but in order to understand the energy changes, we are taking these energies one by one. Okay, so what we are trying to do, we are trying to give lattice energy, and that lattice energy is going to break the Na plus and Cl minus ions, right? And when these Na plus and Cl minus ions break, okay, into gaseous form, they get separated, and then you put it in water. Okay, when you put it in water, we discussed last time. Okay, you get hydration enthalpy. Okay, so you get hydration enthalpy. It is represented by H, energy which is released when the cation or when an anion is put into water. Hydration enthalpy, delta H, hydration of Na plus delta H, hydration of Cl minus. Okay, because both Na plus and Cl minus ions are there, right? So both will get surrounded by water and they will release the heat. Why NaCl becomes soluble? Because this heat which is liberated, this has a negative sign, it comes out, and this heat is required to break. So this has positive sign. Positive sign means you have to give the heat. Negative sign means it is liberated. It is released. So why NaCl is soluble? Okay. Can we compare these values, Fatima beta? Can we compare this lattice energy and this hydration enthalpy? Yeah.
Yes.
So which one which one should be more so that the NaCl can get dissolved? Which one should be higher? Yeah.
Negative.
Hydration enthalpy. Yeah, hydration enthalpy. It is just like business. Okay, if someone starts a business, he puts some money. Okay, into the business. Okay, and then he get returns as profits. When a business will run, if the profit earned is more than the investment, right? Similarly, here also, when an ionic compound will be soluble, if the hydration enthalpy released is more than the lattice energy which is given to break the ions away from one another. Is it clear? Okay. Yeah, so NaCl is soluble because its hydration enthalpy. Hydration enthalpy will be the due to the hydration of Na plus and due to the hydration of chloride ion. Okay, it will be some. It is more than the lattice energy which is required to break that ionic crystal. Okay, so but not all the salts are soluble, right? Not all the salts are soluble. There are some salts which are insoluble. So what reason could be given? Like barium sulfate is there. It is white precipitate. It is insoluble. Okay, why? How can you say that? The hydration enthalpy, hydration energy is not sufficient enough to compensate for the lattice energy. That's why it is insoluble. Okay. So I hope this is clear, right? So I hope you have noted down.
Yes, sir.
So this is insoluble means hydration. I can write hydration enthalpy as He is smaller than lattice energy. Lattice energy is the energy which is required to break. That is more. So hydration energy which is released is less, means the lattice cannot break on its own. Okay, so that's why it is insoluble. So let's move to the next page. Okay, now we will study the reaction with air. Okay, air consists of oxygen, and reaction with air means what? Formation of what? When a substance react with air, what will form? Tell me. If something burns in air, what it forms actually? It forms oxides. Yeah. Okay. Suppose if we burn carbon, what it forms? It forms oxide, right? If we burn sulfur, okay, what it forms? It forms oxide, right? So with reaction with air, air contain oxygen, okay, and it means the formation of oxides, right? So reaction with oxygen or formation of oxides we will study, and that comes under reaction with air, right? Formation of oxides. Mainly it is oxide, and air also contain nitrogen. So if something reacts with nitrogen, it may form nitrite. Okay, it may form nitrites. Okay, so let's get into the detail. Okay, what is the reaction? Actually, alkene metals are very reactive. Okay, they can't be kept in air because no, they are not like iron or silver, which you can keep outside and they will not burn on their own. These alkali metals are very reactive and they will start reacting with the oxygen. They will start burning, right? So you can't keep them in air. What you do in order to protect them, you store them under kerosene or paraffins. Okay, kerosene is petrol-like substance, gasoline-like substance, and that cut off the supply of air. Okay, so how you store alkali metals? You store alkali metals under kerosene. Okay, because they have a tendency to react with air. Stored under kerosene, right? So what is the reaction which occur if you take them out and if you keep them out for a long time? So they occur in a slightly different manner. Lithium, if you take lithium, Okay, when it comes in contact with air, it forms oxide. Okay, oxide is what? Li2O, right? Oxide, lithium is +1. Okay, like other alkali metal. Oxide, oxygen. Oxygen, the atomic number is 8. So oxygen will gain 2 more electron. Why it can gain 2 more electron? So that it can have 10 electron just like neon. Okay, so when it gain 2 more electron, it will acquire -2 charge. Okay, and lithium, how many lithium cations are required to combine with oxide ion? 2 lithium. Okay, that is Li2O, right? That is a lithium oxide. Actually, when the reaction happens, what happens is the lithium, you have taken 4 lithium. Okay, so lithium is going to release electron, that outer electron which we have seen last time. Do you remember that? So it will release, each lithium ion is going to release 4, means 1 electron, so total 4 electron will be released. And you have taken oxygen. Each oxygen atom, in order to gain noble gas electronic configuration, it will accept 2 electrons. So each oxygen, there are 2 oxygen atoms in oxygen molecule, so I should give them 4 electron and they will form 2 oxide ions, right? So lithium form monoxide. Just write it. Okay, this is very important. Clear?
Yes, sir.
Monoxide means this. This is monoxide. Means oxide ion, single oxygen atom with -2 charge. Okay. And sodium will form peroxide. What do you mean by peroxide? Yeah, just try it. What do you mean by peroxide ion? Suppose, okay, this is oxide. Peroxide is, there are 2 oxygen atoms having -2 charge. O2 2- is peroxide. It will be like this. Okay, it will be like this one. This is the peroxide. Okay, there is O- joined by a single bond. This is peroxide. This was oxide and this is peroxide. This is peroxide ion. Okay, so in condensed way, I can write it as O2 2-. Okay, actually it is O- and O- connected by a single bond. So sodium form peroxide. So actually you take oxygen because air contain oxygen, and you take 2 sodium atom. Each one will give 1 electron. Okay, and you will have 2 sodium plus ions, and oxygen after gaining 1 electron, both the atom here they are gained 4 electrons, so they completely broken down to 2. Okay, and but in this one it will accept 1 electron and it will form O2 2-, right? So you don't have to write the charge, but keep it in mind. Okay, it is O2. So this is 2 plus and this is 2-, right? So sodium form peroxide and rest all will form superoxide. Okay, this is a very important thing. What is superoxide? Superoxide, peroxide, oxide is 1 oxygen atom with -2 charge. Peroxide is 2 oxygen atom with each one having -1 charge. So total it is written as O2 minus. And rest all alkali metals means after sodium means there is a potassium. Okay, potassium, rubidium, cesium. Okay, so rest all. And rest all consist of potassium, rubidium, and cesium. They will form superoxide. So what is superoxide? Okay. So superoxide is O2 with -1 charge. Okay. How many electrons will be there on this superoxide? Superoxide actually oxygen molecule will have 16 electrons, right? 8 into 2. Each one having 8 to the 16. And if you put one minus extra, means there is one electron extra. So it will have 17 electrons, right? So if a substance is having odd number of electrons, unpaired electron, that electron is a charge and it rotates on its own axis. So if a charge rotates on its own axis, it become magnet. It acquire magnetic character. And if there is a single electron, that substance will behave as a magnetic character, single unpaired electron, right? So these superoxides will be paramagnetic in nature. Paramagnetic means they have this unpaired extra electron which is not paired to anyone. Okay, and because of this unpaired single electron, okay, that they will behave as magnet, they will be attracted by magnetic field. So you can write paramagnetic, PARA. Paramagnetic means the substance which is magnetic in nature, which is attracted by the magnetic field. Okay, it is a substance which contain unpaired electrons, single electrons. So superoxides will be paramagnetic, and this single electron, just like we have seen in flame color last class, it can get excited to higher energy level, so it will exhibit color. So they are colored, right? So potassium is there, rubidium is there. Okay. This is Rb plus and O2 minus. Cesium is there. Cesium will also form peroxide. Superoxide. While sodium will form peroxide, peroxide, and superoxide. Remember it in this way. That oxides are O2 minus, peroxides are 2 oxygen with -2 charge, and superoxides are 2 oxygen with -1 charge. Okay, and these two will be dimagnetic. Diamagnetic means they have all electrons paired because you have added electron in the multiple of 2. So all electron will be paired in oxide and peroxide. So because of the pair electron, that magnetic character of the electron cancelled. So they will be diamagnetic and this one will be paramagnetic, right? Is it clear? Any doubt in this?
No, sir.
So why they form oxide, why they form peroxide, why they form superoxide? It is actually based on their stability and their tendency to give electrons. Lithium can't form peroxide because it is a small atom, and a small atom, if you have peroxide which is made up of 2 atoms, or superoxide which is made up of 2 atoms, the lithium is going to break. Okay, so lithium is not stable with peroxides or superoxides, so that's why the lithium form oxide only. while sodium and potassium, rubidium and cesium, they can form, sodium can form peroxide and potassium and rubidium will form superoxide. Okay, is it clear? Any doubt in this, Fatima?
No, sir.
Okay, shall we proceed ahead? I hope you have noted down.
I've noted it down.
Okay, in case if you have missed something, do inform me, right? So let's move ahead to the next slide, and it is about their nature. They are actually all basic in nature. Or alkaline, because they are soluble in water, so alkaline is the word which is used in nature. So when you dissolve them in water, okay, they are going to release hydroxide ion, right? So hydroxide ion, suppose if you take lithium oxide or sodium oxide, sodium form peroxide, but if you heat it strongly, it breaks it from oxide. Okay, potassium oxide, potassium forms superoxide, but if you heat superoxide, it will form oxide. They are all alkaline, and their alkaline nature increases down the road. The basic character increases, right? So how can you show them that they are alkaline? Suppose if you take sodium oxide, if you put it in water, so this is the oxygen atom which is oxide, and this is the oxygen atom which is water containing 2H plus. So what they will do, they will share 1 H plus among themselves. Okay, so you have 2 Na plus and 2 OH minus. Okay, so this is sodium hydroxide and this is alkaline in nature. Okay, we know that it is bitter in taste, soapy touch. You might have studied in your junior classes the characteristics. Okay, and because it is giving this OH minus and hydroxide ion, so it is an alkaline substance, right? And now reaction with air will not be complete if we don't consider the reaction with nitrogen. So if you react with nitrogen, actually the reaction will be difficult. Why? Because nitrogen is a little bit less reactive. Both the nitrogen atom are connected by a triple bond. So reaction with N2 will lead to the formation of nitrites. Formation of nitrites, like oxides. Oxygen was having 8 electron and you added 2 electron more. Okay, and that form oxide ion. Similarly, nitrogen is having 7 electron. The atomic number is 7 for nitrogen, and in order to make it 10, you have to add 3 more electron, right? So it will form nitrate. Okay, so only lithium form stable nitrate. Only lithium forms stable nitrate. Okay. And what is going to be the formula of lithium nitrate? Fatima, can you try? I can give you a hint. Lithium is Li plus and nitrate is N3 minus. So what is going to be the formula of lithium nitrate? Yeah. Can you tell me? Yeah. Very simple. Nitrate is -3 and lithium is +1. Okay, so you require 3 lithium ions to combine with 1 nitride ion because -3 and +1. So what is going to be the formula? Fatima, Li3N, right? Lithium nitrate. And lithium being smaller, it is able to combine with the nitrogen very strongly. Okay, and that's why the lithium nitrate is stable. But for other elements, the nitrites are unstable. Okay, clear? Because of the larger size, they don't they don't have much attractive force, and that is why they do not form nitrates. So sodium nitride, Na3N, K3N, they do not exist. Actually, they are unstable. Is it clear?
Yes, sir.
Okay. Just one more thing. Actually, these oxides and superoxides and peroxides, they can absorb carbon dioxide. Okay. So they are used in submarines because submarine, when it goes inside water, it can't take fresh oxygen. Okay. And whatever the people which are there inside it, okay, they are exhaling carbon dioxide. So these superoxides are used in air purifiers. They are used in air purifier to purify air. Okay, how they purify air? These superoxides, okay, O2 minus, they react with, they absorb carbon dioxide and they release oxygen. Okay, what happened to this carbon dioxide? Actually, this form carbonate. For example, so potassium carbonate is there, which is solid. Okay, so this they themselves form carbonate by absorbing oxygen. Sorry, absorbing carbon dioxide and release oxygen. Okay, so they are used in air purifiers, right? Okay, so this is an important thing. Only lithium form nitride, oxides, sodium form oxide. Sorry, lithium form oxide, sodium form peroxide, and potassium, rubidium, and cesium, they form superoxides. Okay, nitride, only lithium forms stable nitride. That's it, right? Superoxides are used in submarine for the purification of air because they absorb carbon dioxide and release oxygen. These things you have to keep in mind. That's it. So let's move ahead. Shall I proceed to the next slide?
Yes, sir.
Okay. Yeah. So now you have uh, oxides, then you have hydrates. Okay, so these metals, alkali metal, when they react with hydrogen, okay, they form hydride. Reaction with hydrogen, these metal hydrides are salt like hydrates because metals are electropositive, so they will have positive charge. Okay, and hydrogen will have negative charge, right? Ionic hydrates. Ionic means salt-like. Salt-like means there is a cation. The cation is actually the metal ion. It is lithium, sodium, potassium. Okay. And the anion is the hydrogen ion. And how the hydrogen ion is formed? Because H2 molecule is there. These two alkali metal atoms are going to release two electrons, one each, and they will be accepted by hydrogen. They will turn to H minus. Okay, that's how you will get metal hydride. These are ionic. And what is going to happen if you put these metal hydrides, okay, in water? They react with water. React with water, right? And what you get when they react with water? When the metal hydride react with water, what you get? Suppose if you take sodium hydride, and this is Na plus and H minus, okay? And if you react it with water, okay? And what is going to happen? Water you can think as H plus and OH minus, okay? So I'm writing below it, there is an H plus and there is an OH minus in the water. So H plus, while reacting it with water, whosoever is the minus charged, you have to connect H plus to it. You have to connect it to H plus. And whosoever is plus charge, positively charged, you have to connect OH minus to it. Okay, what you are going to get? You are going to get NaOH and hydrogen. Okay, what you are going to get? You are going to get NaOH and hydrogen. So hydrogen gas will be liberated. These hydrogen gas is highly inflammable and it can catch fire. Okay, do remember this. So these hydrides are ionic in nature, means there is a cation, there is an anion. Okay, you have to heat them so that they can react, and when they react, okay, they liberate hydrogen gas. Okay, is it clear? Fatima, any doubt in this?
No, sir.
Okay, very good. So this is the reaction. Reaction with water we already discussed, that when you put them in water they melt and they float on the water, and reaction with water, they also liberate hydrogen, right? So these are the main reactions of alkali metals. Right now, there are certain compounds which you have to remember of these alkali metals. What are these compounds? These compounds are NaOH, right? This is actually sodium hydroxide. Okay, and what is baking soda, which we use to make cake? What is the formula for baking soda? Can you tell me? Yeah. Any idea, Fatima? What is baking soda?
Sodium
Hmm?
Sodium bicarbonate and
Yes, exactly. Sodium bicarbonate. Yeah, very good. NaHCO3. Okay, this is baking soda or sodium bicarbonate. And what is washing soda? Yeah. What is the formula for washing soda? Yeah. It is sodium carbonate, right? Okay, and how we use it, why we use it in washing? Actually, washing, it if you use this washing soda, if you add it, it will help calcium and magnesium. It will remove the hardness of water. Okay, hardness due to calcium or magnesium salts are there. Okay, so calcium and magnesium salts will be there, right? And when you put this sodium carbonate, actually it is washing soda. This is the hardness of water. Okay, and actually if there is a hardness, if the water is saline, it can't be used for laundry purpose, because the soap, when it combines with this calcium and magnesium ion, it settles down. So the soap becomes ineffective. It can't be used to wash clothes. Okay, so you have to remove these calcium and magnesium ions. Okay, so you put this washing soda, right? And when you put this washing soda, the carbonate ion combined with the calcium and magnesium, it forms CaCO3, okay, and magnesium carbonate. And why I put this arrow? Because they settle down. Okay, so calcium and magnesium ion, they settle down, they form precipitate, they are removed from the water. So hardness is removed. Now that water becomes suitable for washing. Okay, and why we use baking soda or sodium bicarbonate? What is the purpose? Yeah.
It may like to make it
Hmm.
and cake, like to make it
Yeah,
dry.
it make cake porous. Okay, it make bread porous. Okay, it makes it soft. Yeah, very good. So actually, what is the reason? Suppose if you heat it, okay, heat it, it decomposes to Na2CO3 plus CO2 plus water. So cake, if the dough is there and the dough will be very hard upon baking. So if this baking soda is there, it will release carbon dioxide, small bubbles of carbon dioxide will form. Okay, and that will make the cake softer, and the cake will have small porous holes. Okay, so it is used in baking. Okay, sodium hydroxide is having a lot of multiple uses in industry. Okay, so just we can quickly go through the process of making. Okay, how sodium hydroxide is made. So actually you take sodium chloride and you do the aqueous solution. Means aqueous solution means in water. Okay, and you do the electrolysis. Okay, so electrolysis, what actually is, you put anode, you put cathode. Okay, right? So whatever the anions will be there, they will get attracted toward the cathode anion, and whatever the cations will be there, they will get attracted toward the cathode. Okay, so cation is sodium plus, right? Because we have put NaCl into water, but sodium plus actually will not go and take electron, because sodium plus is already, sodium atomic number is 11, and it has released one electron and it has become Na plus. Na plus is quite stable. It is because it is having noble gas configuration, so it will not react and will become again unstable by accepting an electron. Now who is going to react? We are having water also, because this is aqueous solution. So water is having, we can think as H plus, and we are having OH minus, right? So who is going to go and take the electron from the cathode? H plus. It is the H plus. H plus will go to the minus electrode, negative electrode, cathode. It will accept an electron. Okay. It will release hydrogen gas. Okay. It will get reduced. It will become positive, will gain electron. It will become hydrogen atom. It will become hydrogen gas, right? And what happens to anode? I will write equation here. At anode. Okay. Anode is positive electrode. So positive electrode Cl minus will get attracted towards it. When it goes to the positive electrode take away its electron. Okay. So when you take out two electrons, they will become two chlorine atoms. And two chlorine atom will join together, so chlorine gas will be liberated. Right? Similarly, what happens at cathode? Cathode is negative electrode, and cations get attracted because it is negative, so it will attract cation which are positively charged. So who is going to go at the cathode? No, Na plus will not go because it is already very stable. From water you can think as H2O, which will have H plus and which will have OH minus. Okay, so H plus will go and accept the electrons. So 2H plus will accept two electrons which were released at the anode. They will come through the wire. Okay, they will come here and they will be accepted by 2H plus, and this will form H2. So H2 is liberated at cathode, and at anode chlorine is liberated. And what is left in the solution? Okay, OH minus is left in the solution, Na plus is left in the solution, right? And what you get in the solution? In solution, we get NaOH. So what all things we are getting? We are getting chlorine, we are getting hydrogen at cathode. Okay, and in the solution we are getting NaOH. NaOH is alkali, Cl2 is chlorine. So this process is known as chloralkali process. Okay, clear? Any doubt in this?
No,
Fatima?
sir.
Okay, yeah. And how you are going to make carbonate and bicarbonate? That is very simple. What you do is carbonate and bicarbonate you can make by using solvay ammonia process. Okay, solvay ammonia process. Okay, what you do is you take ammonia, NH3, which is a gas, you put it in water, and you put carbon dioxide, which is also a gas. Okay, so we know that carbon dioxide, when you put it in water, it is carbonic acid, right? So carbonic acid, you know that soda water is there, in cold drinks it is there. Okay, that is actually H2CO3, right? So that is an acid. Okay, when we drink Coke or some Pepsi, and we find it acidic. Okay, it is having this carbonic acid into it, dissolved in it, and that is you might also have seen that when you open its lid, because of the pressure is released, and you see the bubbles coming out. Okay, that is because of that carbon dioxide only. So it is H2CO3, right? Carbonic acid. This is an acid. Ammonia is a base. So ammonia, if it is a base, acid and base will react. They will form a salt. You will have NH4 plus and HCO3 minus, right? So this is ammonium bicarbonate. Okay. And when ammonium bicarbonate, when you put NaCl into it, NaCl is common salt. So you get NaHCO3, that is sodium bicarbonate. That's how you get sodium bicarbonate. Okay. And when you heat it, you can get this Na2CO3. You put it in water, you crystallize it back. So you get Na2CO3.10H2. Okay, hydrated salt. That is your washing soda. Is it clear? Any doubt in this? Fatima, any doubt?
No, sir.
Okay, I hope you have noted. Shall we proceed ahead to the next slide?
Yes, sir.
Anything which is okay? Yeah, anything. If it is not understood, you can ask me anytime. You can stop me anytime, right? If you want to clarify anything. Okay, let's move to liquid ammonia solution. Okay, this is some different thing. Just some questions sometime come on this, right? And this is liquid ammonia solution of alkali metals. These are actually blue colored solutions. What happens is when you put sodium in liquid ammonia, NH3 is a gas actually, but when you cool it, it becomes liquid. Okay, so what happens here is you get Na, we know that all alkali metals have that one extra electron outside. They release that electron, okay, and they form Na plus, okay, and that electron is separated. Okay, so actually this Na plus is there and the electron is there. Actually, what is going to happen to these? We have seen when you put these ions in water, what happens? All the water molecule get attracted toward that ion and they surround that ion and they make it stable, right? So in the same way, here you are not having water, but here you are having NH3 molecules. So this ammonia will be surrounded by some, this Na plus will be surrounded by some ammonia molecules. I am writing it as X ammonia molecule, some X number, okay, of ammonia molecule will surround this Na plus ion, and this electron is there, that will also not remain alone. It will be surrounded by some, I'm writing it in a general manner, okay, and Y number of ammonia molecules, right? And these are ammoniated electrons, okay, which are surrounded by. So how it happens actually, and this solution is blue colored solution, blue colored. Actually, this blue color is because of the presence of that unpaired electron, which absorbs energy and release. Okay, blue colored solution, and because it is having unpaired electron, just now in the last slide we discussed these unpaired electrons, single electron, they rotate and on their axis, and when a charge moves, it generates a magnetic field and they behave like a magnet. So it is paramagnetic. Paramagnetic means which are attracted by the magnet. Okay, diamagnetic means which are not attracted by the magnet. So these are paramagnetic solutions. They are magnetic in nature. They are attracted by the magnetic field because of the presence of unpaired electrons. And these Na plus is there. Okay, what is this X NaC? What it means, I will show you. Actually, this sodium plus ion is there. Okay, and NH3 ammonia molecule is there. Okay, so nitrogen is having slight amount of negative charge. Okay, it pulls electron from the hydrogen. It is more electronegative. It has tendency to attract electron. So because this so nitrogen is having negative charge, it will get attracted towards the sodium ion. Okay, and that it forms a layer of solvent. Solvent is this ammonia only. A layer is formed around the sodium ion. Okay, and that's what X can be a very large number. This layer maybe one layer, two layer. Okay, because of the ammonia molecules are surrounding this sodium ion due to this attractive force between Na plus and N minus. Similarly, what happens to electron? Does it remain alone? The answer is no. Electron is a very small particle, subatomic particle. It is having a negative charge. Okay, and the same thing happen with electron also. But electron cannot attract N minus because electron itself is a minus, negatively charged. So what happens is it will attract this H plus. So nitrogen was having negative charge, but the hydrogen was having positive charge, right? So it will attract hydrogen towards itself. The ammonia molecule has both type of charges. It is having partial negative charge, partial positive charge. So when it comes to stabilization of electron, ammonia molecule will bring in its hydrogen atom facing towards the electron. Okay, and that's how the electron will get stabilized. Okay, these solutions are very good reducing agents. Okay, because they have a lot of electrons and they can reduce other metals or other compounds can be reduced by these solutions. Is it clear? Any doubt on this? Liquid ammonia solutions?
No, sir.
Okay, and when you put in more metal into it and dissolve it, okay, the solution become thick, it become concentrated, just like the sugar solution. If you put more sugar, initially when you put less sugar, the solution is dilute. If you put more sugar, the solution is concentrated. So if you put more sodium, it will dissolve, metal will dissolve in this liquid ammonia. Okay, and it will become concentrated. Okay, and it also changes its color. It become brown in color. Okay, because a lot of electrons are there, and these electrons will get paired, and because of that it will also change. A moment will come when it will change its, when it become brown color, that moment all the electrons get paired up. Okay, and it become diamagnetic also. Diamagnetic means the substance who is not attracted by the magnetic field. It happens when all the electrons are paired up. If you have unpaired single electrons which are alone, then the substance will show magnetic behavior, paramagnetic. It will be attractive. But if you are putting more and more sodium, more and more sodium, more and more electrons are going to come and join these electrons which are already there. So what is going to happen? They are going to form a pair, and when they form pair means their magnetic character is, because in a pair one electron is spin in clockwise direction, another electron will spin in anti-clockwise direction. Okay, and these two electrons have opposite spins, and that's why they cancel their magnetic behavior. Okay, so when you have more concentrated solution, it becomes brown in color, copper brown. Okay, and it loses its magnetic character. it becomes dimagnet. That's it, you have to remember. Okay, clear? Just very small questions will come. I hope you will be able to answer, right? Is it clear? Any doubts in this, Fatima?
No, sir.
Okay, so let's proceed ahead. Okay, and then we can move to group 2, alkaline earth metal. After this, the last thing in group 1 is diagonal relationship. Okay, that is going to an abnormal behavior of the lithium. Okay, this you are going to observe everywhere. The first element of each group, okay, which is lithium here, okay, that will show some abnormal properties, which will not be matching with the properties of the rest of the elements which are below it. Okay, this is called abnormal behavior or anomalous behavior, right, of the first element of each group. So it doesn't resemble with respect to its properties with the other elements which are lying below it. So this is one thing. The second thing is it, on the other hand, it doesn't resemble the elements of its own group. Instead, it resembles the element of the next group which is placed diagonally. Okay, so lithium, for example, I'm going to move to the next slide. Okay, so suppose if you have lithium, sodium, potassium, rubidium, and cesium. Okay, this is group 1 which we are discussing right now, and the group 2 is beryllium, magnesium, calcium, strontium, barium, right? So lithium shows anomalous properties, abnormal properties. So we are going to discuss anomalous behavior of lithium. The properties of lithium are somewhat different from the properties of the rest of the elements present in this same group, group 1. Okay, and we are going to discuss diagonal relationship between lithium and magnesium. So similarly, the beryllium will also show abnormal properties, and its properties, instead of resembling with the properties of the elements of its own group, it will resemble aluminum, which is the element belonging to next group. Okay, and which is placed diagonally. So this is everywhere. This is known as a diagonal relationship and anomalous behavior of lithium, means abnormal behavior of lithium and diagonal relationship. Okay, why it happens and what are the abnormal properties of lithium? Okay, why why it is there? Okay, some of the properties we already discussed. So first is lithium is small in size, that we know. Okay, and due to its small size, it exhibits high melting point with respect to other elements. Lithium is having high melting point and it is harder. Harder than other metals of group 1. Sodium, potassium, rubidium, they are very soft and they can be cut with a knife. Okay. So lithium is bit hard. The reason is very clear. With the size is small, and because of the small size, the atoms are going to attract each other more strongly, and so it will have strong metallic bond. If the metallic bond is strong, then you can explain all these properties, right? It will have higher melting point, mean they will not melt easily. They are harder. Okay, it is harder in nature, while other alkali metals are very soft. Okay, cesium we have seen. The melting point was only 28.5 degrees. Okay, that was around the room temperature. It melts in our hand only. Okay. So another thing is, which is also related to the same thing. This is the anomalous behavior of lithium, which we are discussing right now. Lithium is very less reactive, or we should say only less reactive, okay, as compared to other alkali metals. The reason is same, because of the small size, the atoms are attracting each other very strongly, and in order to react, you have to separate each and every atom. Okay, then they can react easily. But if they are not getting separated from one another easily, means what? Means the reactivity is low. But on the other hand, it is a very strong reducing agent. And that's why we know that lithium is used in our mobile phone batteries, and all the nowadays batteries which are we are getting are lithium ion batteries. Okay, it is a very good reducing agent. So what is the reason for it? Okay, these two things appear to be mutually contradictory to each other. It is less reactive, okay, because you have to separate the atoms away from one another in order to react them. Okay, but if it start reacting, it is a very strong reducing agent, and it gives electron very easily. Okay, and it is in fact the strongest reducing agent, okay, in the periodic table. So lithium does not want to gain electron. Okay, reduction is loss, gain of electron. So lithium itself doesn't want to accept electron. Okay, and doesn't want to accept electron minus 3.04 volt. This is experimental value. Don't have to worry about this, how it came. Okay, we will discuss it in class 12, right? So lithium doesn't want to accept electron, and that's why its electrode potential is minus 3.04 volt. But it wants lithium plus doesn't want to gain electron, but lithium wants to lose its electron, and that's why it is a good reducing agent. And the one who loses its electron easily is a good reducing agent. So lithium, if I write the same thing in this manner, okay, is it clear, Fatima? If I try to write it this way, so this lithium, sorry, lithium plus an electron. So lithium is a good reducing agent, means it has tendency to lose electron. Reducing agents are the one who can give their electron to others. So this is going to be positive, means lithium want to lose electron. Okay, it is a very good reducing agent. So what is the reason? It is high hydration enthalpy. Okay, we discussed in the last class that it was having a very small size. Okay, and because of the small size, it was gaining electron. It was attracting water molecules, and that helped the lithium to lose melt, and that provided the energy to lithium to melt away and to give its electron. Okay, so overall it is small in size, that is less reactive, but when it gives its electron, it has a maximum tendency to lose electron. Okay, that's why it is positive. But if you same thing, if you show it in a reverse way in which you are giving electron to lithium, that will not happen, and that's why it is negative. Is it clear, Fatima? Any doubt in this?
No, sir.
Okay, and lithium, because of its high hydration enthalpy, it form hydrated salt that we discussed. Okay, form Li, Li plus, form hydrated salt. Hydrated salts means they can lose, means it can attract water molecule, and that today only we discussed it can form. So lithium salts, if you keep it in air, what they will do, they will absorb, keep on absorbing moisture, and that moisture is going to get embedded in the crystal as two water molecules. Okay, and the salt will become hydrated salt. Okay. The other thing is the lithium actually is a small ion. So if you have a small ion, then it is going to form a stable compound with small ions, anions, but it is going to form an unstable compound with larger anions, because if you have a small cation and a larger anion, what is going to happen? A mismatch will be there, and larger anions are going to break away. So larger anions, so we discussed smaller anions like Li3n was stable. This was nitride ion. Okay. Okay. But lithium carbonate, okay, Li2CO3, upon heating, it breaks. Or lithium hydrogen carbonate. Sodium hydrogen carbonate we have seen in baking soda. Okay, which was we use it as a white powder. Okay. But lithium hydrogen carbonate cannot be isolated in solid state. You can't get a solid powder after it. Okay, you cannot be isolated in a solid state because it is going to decompose. Okay, it will decompose. Because lithium is a smaller ion, bicarbonate is a larger ion, and there is a mismatch, so it is going to decompose. Okay, so other thing is the other metal when they react with carbon. Okay, so lithium hydrogen carbonate cannot be obtained as solid powder, just like your baking soda, which was sodium hydrogen carbonate. Okay, in solid state it will decompose, because in order to make a dry solid you have to heat it, and if you heat it, it is going to break away. Okay, the next thing is other metals react with carbon. Okay, and with carbon they form the salts. Okay, so other metals react with acetylene, right? This is ethine or acetylene, and when you react with, actually these metals give their electron, they form metal plus, and the electron is taken away by the hydrogen. There are two hydrogen atom connected to the carbon in ethine, right? And the hydrogen is liberated. Okay, so this is ethynate. So other metals form this, but lithium does not form. M is not equal to lithium. Lithium does not form acetylide or ethynide ion. Okay, just remember it. Clear? Okay, because lithium is less reactive, so it will not form. Sodium can react with this acetylene and sodium form a salt with acetylene, this kind of salt. With sodium will form, potassium will form, rubidium will form, but not lithium. This is an abnormal behavior of lithium because it is not matching with the behavior of other elements, right? Okay. And if you take nitrates, so I'm moving to the next slide, Fatima. I hope you have copied. Okay, copied everything.
Yes, sir.
Okay. So now the next thing is, if you compare the nitrates, okay. So nitrate is having this type of formula, NO3 minus, right? These are nitrates. So alkali metal nitrate is lithium nitrate is going to be this one, sodium nitrate. These nitrate, this is chili saltpeter. Potassium nitrate is Indian saltpeter. Actually, they are used in gunpowder. Okay. So why they're used? Because they, when you heat them, they break. Okay, they break and they give oxygen and gases, and that's what gunpowder. The purpose of gunpowder, it explodes. Okay, so lithium nitrate, if you take, okay, it breaks if you heat it. It breaks in a different way. It forms lithium oxide and it releases NO2. Okay, okay, and we can balance it to NO2, and these are two nitrogen molecules, two NO2 oxide, and there is oxygen also which is being liberated, right? Clear? So there are 6 oxygen atoms. So when you heat it, it breaks into oxide. It gives a brown colored gas, nitrogen dioxide, NO2. Okay, it gives oxygen. Okay, and that's why it is, because it is, just now I told you, lithium is very small ion and nitrate is a bigger ion, an ion. Okay, so when you have a smaller cation and a bigger anion, they are going to break away and decompose. Okay, but the way of decomposition is different, right? If you take sodium or potassium nitrate, they are going to decompose in a different manner. NaNO3, if you take, if you heat them, sodium is going to form NaNO2, sodium nitrite, and it is going to give away oxygen gas only, right? So this is an abnormal behavior of lithium. Okay, is it clear? One, we discussed that lithium form nitrite, sodium, potassium do not form nitrate, they are unstable. Okay, so this is the way in which the lithium nitrate and the sodium, potassium, rubidium nitrate break away. Lithium nitrate give two gases, NO2 and O2. Sodium nitrate is going to give only oxygen, right? The next thing is diagonal relationship. Okay, just quickly we can go through it. Diagonal relationship, actually it occurs diagonal relationship with magnesium. Lithium is there. Okay, so if you come here, its size is going to, if you move to beryllium, its size is going to get reduced. Okay, because of more electron in beryllium. Lithium is having 3, beryllium is having 4 electrons. They are going to feel more attractive for, that's why size reduces. And when you go down, there is an increase in shell, the size again increases. Okay, so lithium and magnesium will have approximately same size or same charge to size ratio. Due to which they exhibit same kind of behavior. Okay. And the similarity in behavior is known as diagonal relationship. And what is the reason? Main reason for this diagonal relationship? It is the same charge to size ratio, right? So we have to support, okay, we have to support this statement by giving examples that they both behave in a same way. Okay, for example, just now we have seen lithium forms nitrate. Only lithium formed nitrate among all alkali metals, Li3N. Okay, and magnesium also formed nitrate. It also formed nitrate, but its nitrate formula magnesium is actually +2. It is alkaline earth metal. So it is +2 and nitrogen is -3. So you cross multiply the number of ions with the charges Mg3N2. Okay. So here also it forms nitrate. So both okay are somewhat similar. Lithium form oxide, Li2O. Oxide is one atom, okay, having -2 charge. Similarly, magnesium also forms oxide. And what is the formula of magnesium oxide? Fatima, it is MgO, right? And both do not form. Both, there were other kind of substances also. Both do not formed peroxides and superoxides. Okay, is it clear? So because the peroxides and superoxides were larger ions, okay, they were containing 2 oxygen. So larger ions were unstable with lithium. Okay, that was the reason behind the instability of lithium peroxide or superoxide, right? Lithium compounds are somewhat covalent. It is because lithium is a smaller ion, okay, and it is also abnormal behavior, okay, because it doesn't resemble the character of other alkali metals. It is a smaller ion, and if you have an anion, okay, anion, it is going to pull the electron cloud of the anion. Okay, suppose a cation is there and an anion is there, they are not going to remain separated. Instead, they are going to merge together. And if they are going to, because of the pulling of electron, because it is small, we have seen that it has formed hydrated ion, right? So this is the covalent. This is, I'm in this one, I'm showing the overlapping. This is covalent character. Okay, so lithium compound are somewhat covalent, and you might have studied that like dissolves like. Means if it is a covalent compound, it is soluble in covalent compound. It is soluble in covalent solvents, okay, which are similar. So it formed covalent compound. like LiCl is there, okay, LiBr is there, or lithium iodide is there. They are covalent in nature because of the small size that pulls the electron cloud of the anion, and that's how it gets a covalent character. Okay. Similarly, magnesium also exhibits same kind of behavior. Okay. So this is also up to some extent covalent. Okay. So because covalent compound, they are soluble in organic solvents. These organic solvents are actually soluble in what not water. Actually, they are organic solvent is non-polar. Okay, covalent molecules are soluble in organic solvents. Okay, so these are covalent, somewhat covalent, so they are soluble in organic solvent. But if you take NaCl, NaCl is ionic, so cation and anion, they are not going to become soluble in organic solvent. Okay, because of the covalent character, these covalent compounds have covalent nature because of the pulling of electron cloud of the anion by small cation. They are covalent in character, and that's why they are soluble in less polar or covalent solvent, which are actually organic solvents. But water actually is polar solvent. It is having plus and minus charges. Okay, H plus is there, O minus is there. So water is able to dissolve ionic compounds more easily than covalent compounds. Suppose if you take petrol and oil, they are insoluble in water because those are organic, okay, in water. But sodium chloride is ionic, so this ionic compound are soluble in water, right? Covalent compounds are soluble in organic liquids. Is it clear? So both exhibit same kind of behavior. So these are some of the diagonal relationship. Okay, just go through them, and next time we will be starting group 2. Okay, which and hopefully we will be taking less time because many things are common. We have discussed many things in this, right? So we will be starting group 2 because in next block we are having group 1 and group 2. Okay, so today's class was for 1.5 hours, right? Any doubt in this, Fatima?
No, sir.
Okay, so let me end today's class. Bye bye, take care. Okay.
Thank you, sir. Bye, sir.
Okay.